Over the past decade, tanners in many countries of Southeast Asia have installed individual or joint effluent treatment plants to treat the effluent generated in the leather making process. India alone has 16 common effluent treatment systems and over 180 individual effluent treatment plants for Tannery Effluent. Large common treatment plants have also been set up near Shanghai in China and at Samut Prakarn in Thailand. Another is under construction in Kasur near Lahore, Pakistan, and yet another is to be set up at Bata Atta in Sri Lanka. Effluent treatment involves removing the suspended solids and heavy metals, usually by means of chemical precipitation. This physico-chemical treatment results in the production of sludge. Approximately 3.5 to 4 kilograms of sludge, dry matter, is produced from every cubic meter of effluent treated. In many countries where sunlight and land are amply available, sludge from smaller plants is dewatered in sludge drying beds. The most common mechanical sludge dewatering equipment includes a centrifuge, a chamber filter press, and a belt filter press. In many countries, the sludge emanating from Tannery Effluent treatment plants is categorized as hazardous waste since it contains chromium, albeit in its rather benign trivalent form. However, in the United States and many European countries, tannery sludge has been deleted from the list of hazardous wastes. More recently, effective and efficient sludge management has taken on great significance in many developing countries in Southeast Asia. This is the outcome of the strict enforcement of stringent laws governing the disposal of hazardous waste. Under its regional program for Southeast Asia, the United Nations Industrial Development Organization, UNIDO, has launched a number of initiatives designed to help the industry deal with sludge management effectively. Sludge management options fall into three broad functional areas: reducing the volume of sludge generated, converting it into byproducts, and disposing it off safely in a properly developed landfill. Let us take a look at the technological choices under each of these options. Under reduction of volume, the choices demonstrated are partial substitution of chemicals such as lime and alum by polyelectrolyte and anaerobic digestion of sludge. Using polyelectrolytes to partially substitute conventional chemicals such as lime and aluminium chloride helps reducing the sludge volume by as much as 15%. Sludge volume can also be reduced by digesting the sludge anaerobically. This process entails a degradation of organic matter by microorganisms. UNIDO has installed a pilot and demonstration anaerobic digestion unit at the CETP in Vaniyambadi, Tamil Nadu, India. It has a capacity of 5 cubic meters per day, and its primary objective is to show how sludge volume can be reduced. Sludge is taken from the soak and pickle streams for digestion, given its high organic content. The sludge is first settled in a settling tank and then fed into an anaerobic digester that mineralizes the sludge, thus reducing the total sludge volume. Digestion also improves the dewaterability of sludge. Though it is too early to draw any conclusions as to its viability, results to date indicate that depending on the organic matter content in the sludge, anaerobic digestion can reduce sludge volume by 30 to 50%. For conversion of sludge into byproducts, the choices demonstrated are biomethanation and generation of electricity, composting with other organic wastes, and solidification and immobilization of heavy metals. Often, the organic content in primary sludge is not high. In instances where it is low, combining sludge with other organic-rich waste materials can facilitate digestion. An ideal solution is to combine it with fleshings, another organic waste from tanneries that often poses a serious disposal problem. Wet fleshings can be minced and mixed with wet sludge. In addition to helping reduce sludge volume, such anaerobic digestion process also generates biogas, which can be used to generate energy. The sludge from the digester is subsequently dried and disposed of. Set up by the Ministry of Non-Conventional Energy Sources of the Government of India, the Central Leather Research Institute of India and the UNIDO regional program, the pilot and demonstration unit at the CETP in Melvisharam is currently in the process of being stabilized. Its performance will be monitored over the next year. For composting purposes, tannery sludge has to be combined with admixtures with a high carbon content. UNIDO has established a pilot and demonstration unit in Melvisharam where the composting of sludge emanating from the CETP has been attempted. Composting trials were conducted using different combinations. Sludge was mixed with admixtures such as vegetable market waste, green biomass, tannery fleshings, hay, cow dung, etc. It has been proven that effective composting of sludge with these amendments is feasible. 50% of the admixture can be sludge and the other 50% a combination of other wastes. With appropriate amendments, the temperature of the heap rises to over 65 degrees Celsius within the first week. It takes about 55 to 70 days for the compost to stabilize, and the yield is between 80 and 85%. The coarse material is screened out for reuse in the next round of composting. The fine compost is packed for marketing. It has been found that in terms of NPK value, the quality of compost is similar to those of urban compost and farmyard manure. Compost application in both edible and non-edible plants has yielded good results in terms of growth. It is reported that the compost offers good market potential in rural areas in India, and the sales price will help to recover the production costs involved. Following a certain measure of relaxation in legislation pertaining to solid waste and sludge containing chrome in its trivalent form in many industrialized countries, the Government of India has recently issued a notification to the effect that if the level of trivalent chromium in sludge is less than 5,000 milligrams per kg dry weight basis, it will no longer be considered hazardous waste. The long-term behavior of the chrome present in sludge is currently being studied. However, as an alternative mode of sludge utilization, composting is feasible only when the sludge has a low chrome content. This option thus provides tanners with a good incentive to introduce better chrome management systems in their tanneries. For sludge containing chromium at levels more than 5,000 mg per kg on dry weight basis, another option was evaluated, solidifying it and stabilizing it in combination with any other material. Sludge can be solidified with clay or other wastes such as fly ash. The pilot and demonstration work carried out by UNIDO under its regional program established that sludge could be combined with other material in 70-30 ratio. The resultant material was found to immobilize effectively heavy metals such as chromium. The chromium was not found to leach from the compound. The compound was then converted into unburnt bricks. The bricks were chemically stable in as much as no chromium leaching was observed. However, its mechanical strength was inadequate for wider application, a serious limitation for this option. Under the circumstances, the most viable option for the disposal of substantial quantities of tannery sludge that contains chromium beyond permissible levels is a safe landfill. Under its regional program, UNIDO, in cooperation with the local tanners, has set up model safe landfills as pilot and demonstration units in the common effluent treatment plants in Ranipet and Melvisharam. A safe landfill comprises an impervious bottom, generally of compacted clay, and a geomembrane. The geomembrane most commonly used is high-density polyethylene. The objective is to ensure that the leachate from the sludge does not permeate the soil and groundwater. A drainage layer to collect the leachate from the sludge deposit is laid on top of the liner. It consists of 2 layers of gravel of different sizes with embedded pipelines. The leachate is collected via the drainage layer in a collection pit, whence it is pumped to the effluent treatment plant or sprayed back onto the sludge heap. The drainage layer is covered with another layer of compacted clay and a layer of river sand. The sludge is then deposited on the top in cells. After the sludge dumped has reached the full designed height of the landfill, it is covered with an impervious layer. The impervious layer can be clay, with or without a plastic liner. The landfill embankment can be reinforced by laying grass on the sides. A tow drain is provided on all 4 sides of the landfill to carry the surface runoff during rains. The capital cost of the landfill at the common effluent treatment plant in Melvisharam was $8.5 per cubic meter, and running costs are $0.6 per cubic meter of sludge deposited. At present, a safe landfill is a most feasible alternative for disposing of tannery sludge. A manual on landfill for tannery sludge has been published by UNIDO for use by tanners of the region. The proper utilization or safe disposal of sludge generated by effluent treatment plants is important for the future growth of the industry. In many industrialized countries, sludge disposal often costs between $100 and $200 per ton. The UNIDO regional program has attempted to provide the industry in the region with cost-effective solutions to this problem. The initiatives taken by the industry are indeed reflective of the changing times. The UNIDO regional program will continue with its efforts in this direction. It will consolidate its achievements and disseminate the results to tanners in the region.